Hello, and welcome to our presentation. Firstly, we'd like to thank the ISBS for arranging this platform. My name is Simon Augustus, and I'll be presenting our work on how data processing influences interpretation of joint kinetics during the kicking skill. Assessment of kick leg joint kinetics are important for understanding ball kicking skills, such as the rugby place, football instep, and AFL punt kick. Patterns of kick leg, knee, and hip moments in their powers describe how and when specific muscle groups perform work during the kick and can be used to inform empirically grounded training practices. From the top of the backswing, concentric action of the hip flexors and knee extensors initiate the downswing. Then, as the knee extends past 90 degrees, concentric flexion of the hip continues, but the knee muscle moment reverses the flexion and power is absorbed. Finally, the hip continues to generate power upon ball contact, whereas the knee has been shown to reverse to show distinct flexion moment. This mechanism may be indicative of co-contraction of the hamstrings to protect the knee from overextension and the substantial forces experienced upon impact. However, the question remains over these interpretations, as it is acknowledged as very difficult to accurately determine lower leg motion and subsequent joint kinetics near the time of ball contact when conventional motion analysis and data processing techniques are used. This is because the inverse dynamics analysis needed to compute these joint kinetics is reliant on first determining valid input parameters. First, we need to accurately measure ground reaction forces and center of pressure under the standing foot. Second, we need to accurately measure thigh, shank, and foot inertial parameters. Finally, we need to derive accurate segment velocities and accelerations from the marker trajectories. We can do a pretty good job with the ground reaction force and inertial inputs, but there are known problems with estimated segment kinematics near the time of impact. The problem lies with methods of low-pass filtering marker trajectories attached to these segments. See how the filtered data, shown by the bold line, attenuates foot center of mass velocities compared to raw data from approximately 20 milliseconds before the instance of ball contact when cutoff frequencies of 12 and 20 Hz are used. To avoid this distortion, researchers instead tend to truncate data at the start of ball contact, or a few have used advanced time frequency filter methods that raise the cutoff frequency over the duration of the impact to obtain valid velocity and acceleration estimates. As you can see, these improve the calculation of foot velocities compared to the raw data, but no study has investigated how choice of low-pass filter affects estimates of kick leg joint kinetics. It is therefore important to consider how choice of data processing influences practical interpretation of these kinetics. If erroneous methods are used, this might limit our ability to provide useful feedback and understand how skill kickers optimize performance. So, we had 18 footballers perform instep kicks for maximal speed and accuracy. 3D motion data and ground reaction forces were collected from kicking foot takeoff to the end of the follow through. A lower limb marker set enabled production of a 3D model, and joint kinetics were derived using standard inverse dynamics. The filter conditions were chosen either to represent common methods used in ball kicking literature or a novel fractional Fourier method, which we recently showed to enhance measurement of lower leg accelerations during instep kicking. The BW12 and BW18 were examples of filtering through the impact phase with cutoff frequencies of 12 and 18 Hz. The BWEXD truncated data 10 milliseconds before the start of impact, and the BWBC 1 milliseconds before impact. Finally, the FRFF conditions either filtered through the impact or extrapolated the final 10 milliseconds as per the BWEXT condition. Irrespective of filter condition, we showed hip moments reverse to extension in the final 30 milliseconds before ball impact. However, there was some variation in the magnitude of these moments. The free truncation or extrapolation methods all showed smaller extension moments of between 0.1 to 0.9 by the start of ball contact, but the three methods that filtered through the impact phase all produced more pronounced extension moments at this same instance. The same pattern was shown for the knee, with all conditions showing moments reversed to flexion before the start of ball contact. Again, the filter through impact conditions all showed larger flexion moments and power absorption compared to truncating and extrapolating. Since lower leg decelerates suddenly upon impact with a ball, The distortion towards more negative values seen in the filter-through conditions can be attributed to the inverse dynamics, not accounting for the external force of the ball. For example, the fractional Fourier filter, which is sensitive to the sudden deceleration of the foot upon impact with the ball, shows a sudden and large negative spike just before this impact. Whereas the BW12 and BW18 overfiltered the data and showed an earlier but less pronounced distortion. We therefore contend that truncation or extrapolation methods should currently be used to determine pre-impact hip and knee joint kinetics during ball kicking. These are important findings as it influences how the movement pattern is practically interpreted and trained. At the hip, previous studies have exclusively reported that the hip flexors work concentrically right up until ball contact, and it has thus been suggested that training the hip muscles to perform more work may be beneficial for improving ball speeds and/or distance. However, our cohort of kickers mostly reversed to extension moments, even when preferred truncation or extrapolation methods were used. This may be indicative of different inter-individual strategies for performing the kick. Studies by Ball and Atek et al. Have previously differentiated between thigh and knee dominant kickers. Hip or thigh dominant kickers maintain relatively more hip flexion compared to knee extension velocity at ball contact, whereas knee dominant kickers arrest hip motion and show relatively more knee extension velocities by ball contact. It is therefore logical to extend these classifications to include that hip dominant kickers correspond with those that maintain concentric hip flexor work, whereas knee dominant kickers eccentrically decelerate the hip before contact to induce proximal to distal transfer energy to the lower leg. Understanding these differences in strategy may be helpful for informing tailored technical and conditioning practices. As previously noted, maximizing concentric hip flexor work may be appropriate for hip dominant kickers, but knee dominant kickers might benefit from focusing on decelerative capacity of the hip flexors and knee extensors to maximize angular acceleration of the lower leg. The timing of reversal of the knee moment from extension to flexion is also key for understanding ball kicking skills. It occurs around the time of the kicking knee extends past 90 degrees and marks the time where the knee exceeds the concentric force producing velocity of the knee extensors and the knee begins to absorb power. After this point in the kick, any further angular acceleration of the knee is the consequence of passive motion dependent forces originated from anatomically remote sources. In recent years, researchers have highlighted that kicking thigh deceleration, torso acceleration or release of the tension arc, and support knee extension all contribute to extension, knee extension and foot velocities in this final phase of the downswing. Since the previously noted distortions caused by filtering through ball impact also affects the timing of the moment reversal to flexion and power absorption by up to 15 milliseconds, using an erroneous filter method may confound attempts to understand the interactions between whole body motion and kick performance. For example, to induce efficient transfer of energy to the kicking foot, the timings of thigh deceleration, torso flexion and support knee extension must coincide with the instance of the timing of the reversal. Use of a conventional filter method with a low cutoff frequency will make it difficult for future research to explore the interrelationships between these mechanisms and kicking performance in greater detail. In conclusion, due to the confounding influence of ball impact, truncation or extrapolation methods should currently be used to determine pre-impact joint kinetics during ball kicking skills. Filtering through the impact should be avoided, especially with lower cutoff frequencies. And researchers and practitioners should ultimately be aware of how choice of data processing affects interpretation of the skill in question. Future research might consider accounting for the ball reaction force in the inverse dynamics equations. Promising recent attempts have been made to either model or directly measure the magnitude and location of this force upon the foot. If this force could be accounted for, it might reveal how new insights regarding neuromuscular control during ball kicking skills. For example, today it has been impossible to derive valid estimates of ankle joint kinetics. Knowledge of the strategies used to prepare the ankle-foot complex to ensure an efficient foot-to-ball contact might further highlight how skilled players are able to optimize kicking performance. Thank you for watching. If there are any questions, please do get in touch with me using the contact details at the bottom of the slide. Once again, thanks to the ISBS for making this platform possible. Thank you.